This is Lab 1 Measurement. Your first question should be, why are we studying measurement? Measurement is where it all begins. This is roughly how science works. Someone notices that some process happens in a regular, repeatable way and develops a hypothesis that might explain how that process works. Measurements are made and collected as experimental evidence to test the hypothesis, which is refined or replaced based on the evidence. As evidence accumulates, a theory develops in the form of a mathematical model that describes the process. From the theory, predictions are made and verified by additional experiments, more measurements. More refined measurements may reveal additional detail not discovered by earlier work and require further refinement of the theory. That's a crude description of the scientific method, or at least one such method. What you're studying often determines how you study it. All science, engineering, and technology is ultimately based on observation and experiment, and experiments are performed by making measurements. Most of this course is devoted to making measurements to test some of the more important theories in classical mechanics. The goal is to help you develop some intuition for the way things work and how to describe them mathematically. In this lab, you're going to discover how measurements are made and then how to report them. But first, we have to cover some bases. Units. In the lab, there's no question how this is going to work. We use SI units. The United States government gave up trying to maintain the American standard almost 60 years ago. In today's U.S. customary units, the foot is defined as 0.3048 meters. Science the world over is done in SI units. My Subaru is made in Illinois with metric bolts, and since a private company crashed NASA's Mars lander due to a unit error, it's getting hard to find anything meaningful not using a metric system of units. In our case, we certainly don't want to have to start working in ergs and dynes, units that few remember and fewer care about. So we will use SI exclusively. The SI units are based on 7 base units: the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela. The kilogram, meter, and second are going to be our primary focus for this semester. If we get to thermodynamics, we'll see the Kelvin and the mole. The ampere is the hot topic for next semester, and the candela, well, I've never used a candela in my entire life. Having said all that, we're about to do a lab in non-standard units. The SI unit for length is the meter, but a meter's large and measuring small parts with it is inconvenient, so we'll use the more reasonable centimeter and occasionally the millimeter. The same is true of mass. A kilogram is large, and we'll primarily use grams for what we're going to do. It shouldn't be much of a problem. You just have to learn how to shift the decimal point to convert from one to the other, a key advantage to the metric system. Where this gets tricky is in derived units. All the other units we encounter are combinations, but those combinations are valid only for the base units. A Newton is a unit of force. It combines mass, length, and time, kilogram, meter per second squared. But you can't use a measurement in centimeters and get a Newton without conversions. You must be consistent. Technically, you should convert all measurements to the base unit and then combine them, but things are not always so straightforward. For instance, the unit of density is the kilogram per meter cubed, and once again this leads to inconveniently large numbers. The chemists are used to the more reasonable gram per centimeter cubed, and no one has been able to get them to give it up, so it's an accepted, if non-standard unit. And that's what we're going to use in this lab. It won't be a huge problem in this lab, but in general, you should always be wary and be consistent about your choice of units. Now let's talk about uncertainty. The first difficulty we face is that measurements, by their nature, are never exact. They are, in fact, uncertain. And here I mean in a scientific sense, with a mathematical basis. Why they are uncertain is a question for the lecture hall or possibly even a philosophy class, but we're going to be a bit more pragmatic. Modern standards set by international agreement discuss the types of uncertainty, their source, and how to report measurements. I supply links to several pertinent documents that can help you understand the finer points. Unfortunately, the ISO documents are behind a firewall and there is no need for us to pay for copies. The NIST site is much more user-friendly and free. And then there's the math. The uncertainty of direct measurements, things you do with a ruler or a scale, propagates through a calculation or indirect measurement. And that uncertainty has to be calculated as well. We'll avoid calculus, but the calculations might be a little more strenuous than you're used to, so you may want to read through the material ASAP. I'll try to put together a summary for you as well. The physics website, physics.qc.edu, under current students, downloadable documents, and click on our section, has a document called the appendices. Appendix B discusses uncertainty and gives the algebraic forms of the formulas you're going to need, and it gives examples. Let that be your guide. In practice, our concern can be summarized as follows. How uncertain are the measurements we make? That's a function of our tools. How does the uncertainty affect the results of our experiments? That's something you will struggle with for the rest of this semester. How do we report an uncertain measurement? Finally, an easy question. You report measurements as a range, formatted as shown. This says that with high confidence, barring errors, this measurement is between 55.3 millimeters and 55.9 millimeters. That's the best we can do. We set the uncertainty of our instruments, we make measurements with it, and we are promising that we are certain that the measurement is within that range. How you get the necessary values is a more difficult problem, and we'll address it in this lab and the following labs. So let's start talking about tools. In the beginning, human sensors were the tools used for making measurements. They were all we had. The data that Kepler studied in forming his laws of planetary motion came from naked eye observations of the night sky. Galileo, famous for his observations on motion, made them without the use of a decent clock. Some basic tools were developed as aids to the senses, and we still use tools that rely on human sensors to read them, for instance, a ruler or a balance. But it wasn't long before it became obvious that human senses would not be enough, and for the most part, modern measurements are made with sensors. Electronic sensors play a large part in this course. In later labs, you will be analyzing sensor data and even making measurements in software. But as for using basic tools, rulers, balances, etc., that requires hands-on practice, and that's still not possible in an online course. We will have to struggle on. In each lab, we will make an effort to find things that you can measure from home, or at least on your computer. But since hands-on experience isn't possible, I will often act as your lab partner and you'll watch me collect data. In this case, masses and lengths, which you will then analyze. The analysis for this lab is straightforward, consisting of plotting data in Excel, and of course interpreting it. As you watch me make the measurements, you will see me struggle with the limitations of the tools. The real challenge for you will be in dealing with the uncertainty of those measurements. We'll start. I'm going to take you through the use of some of the tools. Procedure 1 is actually you reading a ruler that I'm going to hold on video for you, just for 3 measurements. Don't get excited. The second one is a something you can do at home. Everybody has an AAA battery, and you'll have to find a way to measure that indirectly. I'll talk about it more in the video portion. In procedures 3, 4, and 5, I'm going to give you a set of data. There is no sense in making you read all of the measurements that I'm going to have to make to collect it. And once you got it, you will have to plot it and do some analysis. And again, you'll hear about that later on in the video. And now, what else should, one more thing, the equipment. This is our tools. There's rulers, calipers, micrometers, a scale, and in the background you'll see some samples. Theoretically, there should be a balance here, pan balance, but since I don't have one available and I don't really have the time to sit here and use one, we're going to skip it. It's a little more complicated as far as uncertainty goes anyway. The scale is much easier to use, and that's how I'm going to collect data. So let's make a measurement. The most basic way to make a measurement of length is with a ruler. You've all seen them, wooden meter sticks, plastic rulers with meters on, or centimeters on one side and inches on the other. These are the ones we use in the lab. They're made of tempered steel. They're sold as machinist rules by a reputable dealer. To make a measurement, we first have to line up one end of the sample. The problem is, if I zoom in on this, the end of this, that final space seems bigger than this one. Now, it may be an optical illusion based on the fact that the line here has been cut off, but that's already too much complication for me. I don't want to risk introducing an error that I can't control. So I'm simply not going to use the end of the ruler. That should be something you think about always. I'm going to use 100. Why 100? Because it's easy to subtract. So now I'm going to line it up best I can. There I go. Now I want you to look at something. Watch where it lines up. Now it's physically not changing. I'm panning the camera, not the ruler here. But it doesn't look like the same alignment from this side as it does from this side. That's a perspective effect called parallax. There's no way to correct for it. You just have to be aware for it. Make sure that you are directly above the part and that you are very careful in lining it up. Let me take one fast. There. I think that looks good. So now we have to go to the other end. We slide along the ruler, and we see that the other ruler falls between 148 and 149. We can subtract the 100 off, of course. So this part is 48.8 and something. What's the something is the case here. So your next job is to take that space, that 1 millimeter, divide it up into 10 parts, and estimate with your mind's eye where it falls. So if I look at this, I make sure I'm directly above it, no parallax. That could be, I don't know, I think it's 0.3. So that would make my measurement 48.3. But it could also be 0.2. And to be fair, it might even be a little bit more. It might be 0.4. So that's a range of 0.2 millimeters. If we divide it in half, then our measurement is 48.2 plus or minus 2. Are we all happy that that is a measurement we can be confident in? I think that's a little tight. Most students who lack experience and patience are not going to be able to do that regularly, not with confidence. So I'm going to double it. Let's say that it's plus or minus 0.2. So now my measurement is 48.3 plus or minus 0.2. That's more reasonable. So what does reasonable and confident mean? I said this had to have a mathematical basis. Well, if you look at the NIST document, you'll find that what we're doing here is examining a type B uncertainty. We're using our judgment to declare that the uncertainty is a certain amount. The other way, type A, would be to do it statistically, which is something we're going to give a try in another procedure. But for now, we're in type B land. So that in type B uncertainty, the document tells us that we should assume a normal distribution. And I'm going to have to hope that you remember some high school math and remember a little bit about the normal distribution. The normal distribution gives us a confidence value. Plus or minus one standard deviation gives you 68%. If we say that our plus or minus 2 is a standard deviation, then 68% of every student who measures this should be able to come up with a number in that range. And that sounds good to me. Well, it would sound good if it wasn't the fact that so many students are getting it wrong. We're not testing students here. We're trying to get a measurement that we can be confident in. So let's do the next step from the NIST document, which is to multiply the standard deviation by 2. Our standard deviation that we've decided on is plus or minus 2. We're going to double it to plus or minus 4. Now, can we with confidence say that 95% of students are going to be within plus or minus 4? And yeah, I'm good with that. I think that's very doable. Except we've forgotten something. Let's go back to the other end. So we've been very careful to align this end up to the 100 mark, and we just subtracted the 100 off. But we aligned this by I, and by now you should be realizing that nothing is without uncertainty. So while this looks very good, we have to add some uncertainty. So I'm going to suggest that we add plus or minus 0.1 millimeter for the uncertainty for our alignment on the 100 mark, added it to our 0.4 millimeter uncertainty on another, and we've got plus or minus 0.5 millimeters as the uncertainty for measurements we make with this ruler. That's something we can be confident in. It's something that is repeatable, and that's what's important here. If you look at this measurement, we're now in the land of 48.3 plus or minus 0.5. That's a big range. That's a range from 47.8 to 48.8. Not only should we be sure that all students get in there, it sounds like it's more than it should be. Clearly, this is not below 48. So the problem is there's something else I have to show you. Give me a second to set it up. Here I have a plastic ruler of the cheap kind. You know, the Chinese little dollar store geometry kits that they use in middle school. I can't line it up with the 0 for reasons we discussed before, and even lining it up at 1 centimeter is problematic because the line is so thick, but we're doing the best we can here. And I'm going to hold it there, and now I'm going to, it moved, go back. There, I'm good with that. Now I come down to 15 centimeter mark, which is the length of this ruler. And it's hard to see because of the yellow background, but now I have to go back and do it again. This is the trouble with measurements. There. Now I come here, and my 15 centimeter mark is almost half a millimeter shorter in the plastic ruler than it is in the metal ruler. We have two rulers that give a different dimension. What do we do? Well, for one thing, we can take the cheap dollar store ruler and discard it and go with the fact that this is made by SPI, which stands for Swiss Precision Instruments, though the thing is made in India, and assume that they are giving a better value. But there's still a problem. Here I have another SPI ruler. And there. Once again, I have lined it up and it moved at the 1 centimeter mark. There we go. By the way, they line up exactly here. Maybe they were right all along and we were okay. So let's go to 15 centimeters here. So there we are. And there's still a slight difference here. And if we go further down the line, to the end of the other ruler, we see at 30 centimeters it's almost a 1/4 millimeter. Now we have two rulers between which I have no reason to choose one or the other that give two different measurements. What do we do? Well, it pays to remember that the difference between these two rulers is incredibly small. It's less than 1/10%. Secondly, we're measuring blocks that are only a few centimeters long. And the difference between the two rulers over a few centimeters is negligible. More importantly, that if you're interested in making precise measurements, if that's your business, and in physics that's our business, then you simply don't make measurements with rulers. Rulers are a crude instrument for rough measurements only. That's why we have to assign an uncertainty of 0.5 millimeters to these rulers. Okay, so why does all this matter? What difference does it make if a ruler has a 0.5 millimeter uncertainty? Well, in physics, you may be studying something that is such a small grain, so small in scale, that at 0.5 uncertainty, 0.5 millimeter uncertainty, you simply miss it. Perhaps even for the things we will normally be studying, you'll certainly be less sure that you've actually proven what you set out to prove, or verify what you've set out to verify. To give you a chance to make a couple of measurements and to provide a somewhat more visceral example, let's complete the measurements for this block. So we've already measured the length of this. It's 48.3 plus or minus 0.5 millimeters. Let's get the other dimensions. So I'm going to call that length, and now I'm going to give you the width. Of course, those names are completely arbitrary, but we have to call them something. Let me zoom in. That looks good there. So if I come over here, there. So count the tick marks, estimate the last digit, and apply your uncertainty. Record it. You're going to need it, right? And now the final dimension, which we'll call the height. I line it up, and I adjust the angle, and again, make your measurement. And apply your uncertainty. Okay, so now you have 3 dimensions, and you can multiply them together to get the volume of that block. The problem is that your measurements have uncertainties. And if your measurements have uncertainties, then those uncertainties have to work their way through, what we call propagate through, the calculation. And you are going to have to calculate the uncertainty of the product. Now, the easiest way to do this is to go through the documentation and find the appropriate formula. You should be able to find a formula for multiplying 3 uncertain values. When you do that calculation, you'll get an uncertainty in the volume of this block. Now, I don't want to tell you what this stuff is, because that's something you have to figure out later in the lab, but I will tell you it's made in the millions of cubic meters, and it's about $25,000 a cubic meter. So here's what you do for procedure 1. Take those measurements, record them in your lab report, calculate the volume, calculate the uncertainty of volume. Now you have a range of volumes. Calculate the subtract the 2, the upper and the lower range. And now you have a difference of volume. Multiply by $25,000, and that tells you how many dollars per cubic meter. And as I said, this is made by the millions of cubic meters. In your analysis, you're going to actually show us that you know how to make that calculation. You can type it in if you're willing to do that, not asking for that. You can simply write it out and then scan it. And you can get scanning apps on your phones now, so it shouldn't be a problem. If it is, talk to your instructor. And insert that calculation into your report. And discuss whether or not that 0.5 millimeter uncertainty becomes significant, and whether or not it's worth finding a more precise figure, something with less uncertainty. And that's it for procedure 1. Okay, so we talked about a situation where we have type B uncertainty. Now I'd like to set up a situation where we can demonstrate type A. But type A uncertainty is uncertainty that's derived through statistical means or defined through statistical means. That means I need a lot of measurements by different people. And since for most of this lab I'm going to be providing all the measurements, that's not helping us. I'd also like to find a way to get you to measure something at home. So here's what we're going to do. That is an AA battery. Everybody should have an AA battery. Now the problem with an AA battery is it's round, and there is no way to be sure that you're measuring a diameter. So the only way to do so without an instrument designed for measuring diameters would be to measure it indirectly, and that's what I want you to do. You're going to use a ruler, but you're going to have to find an indirect way to get the measurement from the battery so that you can then measure it by the ruler. Leaving it up to you what you do. It would also be good if you could find a way to reduce the uncertainty of the measurement. These things are possible. You'll have to do a type B analysis, just like I did in the first one. That's why I did it so slowly. We're going to ask you to do it again from time to time. Go through your process, assign an uncertainty to it. And that's going to be type B. And then we'll collect all of the data from all of the students. So all of our students together aren't enough really for statistical certainty, but it will give us a very nice demonstration of how it works. There will be a Google Doc set up someplace. There will be a link with the lab. You'll go there, you'll enter your values for the diameter of an AA battery. At the end, I'll put together all that data, plot something nice, and distribute it around so we can see how type A works. And that's it for procedure 2. I guess I should say a couple of words about the scale. This is a digital scale, so it's your first sensor. And how we arrive at the uncertainty is a little more straightforward. You can see that this is measuring that block as being 43.08 grams. And that's 2 certain decimals. So where's the uncertainty? Well, the uncertainty would be in the next decimal place. And since it can be anything, we can't see it, we'll have to assume that it's plus or minus 0.005 grams. That's 5 times 10 to the minus 3 grams. Small. That's pretty good precision. It's more than good enough for us. That's how I'm going to do everything here. The sensor here is a load cell. Can we see it? Not really. But inside there's a load cell. Okay, for procedure 3, despite saying how bad rulers are at this kind of thing, I collected the data using a ruler and a digital scale. It'll be in the accompanying document. You can cut and paste it here. My point here is there's a few things I want to show you. One of them is a little bit how to prepare a file in Excel to copy and paste into your report. So this is the data. You can copy it right out of the accompanying document. If you want to dress it up a little bit, we could do this. And we'll go to here, merge and center. Let's center it that way too. Let's increase the font to like 16. These as well. We'll increase the font. looks good. Make it a little deeper. So, sample number, mass. And in brackets is the unit. You can't put the unit in the cells. It'll confuse Excel. So the typical way it's done is to just put it once in the header, in brackets, after the title of the header. How do I get it on two lines? Well, we're going to need volume. And volume is going to be grams per cc for cubic centimeter. And if I go here and hit Alt, Enter, it goes down onto two lines. This is not being centered, so let's center it. There you go. Let's make it a little wider. I can grab this button here and make it just a little bit wider. There you go. That's looking good. If you want to put a border, you can right click. I find the easiest way is to go to Format Cells, and somewhere in here it says border. No, up here, border. I'm going to take this one and do the inside of this. And say OK. And then I'm going to take this one, and I'm going to do the same thing. Format Cells, border and inside border. Say OK. And here I'm going to take these, and I'm going to do it again. And I'm going to take a lighter line for the inside and the darker line for the outside. And say OK. This is not the only way to do these things, but this is the way I typically do it. Nor is it completely necessary, but if you want to dress it up, that's the way to go. So how do we plot this? For plots in your physics labs are going to be the same. Insert, scatter plot, the first one only. No funky lines, just points. Now, you're going to get a blank here because Excel's confused. What exactly do you want to plot? You can try highlighting them, but in general, I just find it easy to select data, add, and here I put the series names, mass versus volume. X values I can click on here. The X values are going to be our volume. Enter. That's going to be a problem. And the Y values are going to be the mass. Enter. And I'm going to say OK. OK. So that's a little weird because there's nothing showing up. That's because I forgot to actually calculate the volume. How do I calculate the volume? So I click here in a cell. I want to make a calculation. I hit the equal sign to tell Excel that this cell has a calculation. I want to multiply this times this times, where times is the asterisk, this, and I hit enter. And I get a number. And now I grab this little handle in the corner and I fill down, and it does them all for me. So that's a lot of decimal places. Let's knock it down to say 3. Okay, we'll leave it there. Some of those have 4. You can fix that if you need be. And there you go. Our data shows up in here. So where we get lines is we want to do a regression, and in Excel that's called a trend line. So we add a trend line, and this one's going to be linear since this looks really linear. The question of whether or not to set the intercept to 0 comes up, and if there is no mass, there better be no volume. So I'm going to go with that, and I want to see the equation always, and I want to see the r squared value always. And there we have it. There. And that's the plot that you have to do in Excel. You have to do it several times, but it's generally the same. I didn't put the axes titles here. You can. You can go through the menu system and find the axes titles and fill them in. And it's necessary that you do so. Okay, so that's all I had to really show you here. Now there's something else I want to demonstrate. If I calculate the uncertainty of the volume, right? Because each of these has an uncertainty of 0.05 centimeters. So that it has to follow through here. The way to find it is, well, you can look at the NIST document and try and sort it out. But also you can use the physics website, physics.qc.cuny.edu, current students, downloadable files, 121, and you'll find an appendices. This is that document. You scroll down to Appendix B, which talks about uncertainty. You can do that on your own time. I'm not going into the ins and outs of uncertainty here. That would have to be a separate file. And here it starts giving you how to calculate it. Here, this is a subtraction. Multiplication, that's what we want. We're going to multiply the three values. And there's three examples. And the third one, happily, is for three values. If you want to multiply x, y, and z, then this is the calculation you have to make. So, in general, you're going to do this once per data set. Not a big deal. But in this case, I want to do it for each part of the data set just to prove a point. And rather than try and do that by calculator, I'm going to put this in Excel. So I'm going to choose this, and I'm going to insert symbol delta, insert that, and volume for the volume, and it's going to be grams per cc, and enter. It's trying to split it up, but we're going to do what we did before. First of all, I have to fix that. I somehow got the wrong parentheses in there. And Alt Enter, two different lines there. Delta volume for the difference in the volume. Look better with a space there? I think so. And let's actually make that a capital. There you go. I put my cursor here and I say equals. Telling Excel this cell contains something you have to calculate. So I need a square root. So that's SQRT parentheses. Your opening parentheses. And then I want to do each term. So I want another parentheses. And my first term is going to be x times y times delta z, which is always going to be 0.05. Close that parentheses, and then to the power of 2. So I squared the first term. So I have to add the next term. And now I'm going to do it again. I'll open the parentheses. This time I'm going to take this one times this one times 0.05, close the parentheses, to the power of 2, add it to the final term, open parentheses, this one times this one times 0.05, close the parentheses, to the power of 2, and close that or square root parentheses. That's it. You can pause the video and take a look at that. Would be helpful probably if you had this in Excel. If you can figure out how to store it as a function in Excel on your copy, that would be great too. Anyway, I hit enter, and it's complaining, what did I do wrong? So I'll say okay, because I used the wrong character here. And I did it every time. What did I do? Oh. I've forgotten how to type. Now I hit enter, and I get a value. So, there's a lot of decimal places for uncertainty. But if we're uncertain of this decimal place, how uncertain are we of the next? Doesn't make any sense to have a second decimal place. So here I'm going to go back home, and I'm going to use this to bring it down to one decimal place. And now, because this is Excel, I can do this. Fill. And there's my uncertainty for each calculation. Oddly, they're not the same. And if you look, so here is sample 30 is very large, and it's got a huge uncertainty. What's very small, the first and last are small. They're about the same uncertainty in the volume, and they're much less the uncertainty of the large one. So we have to think about what to do about that. Unfortunately, it's not even that easy. Let's actually do another one. Density. Alt enter parentheses. Oh, I did the density wrong. The volume wrong. Gram per cc. And enter. Yeah, don't say as I do, not as I, whatever. This should be cc. This should be cc. And this should be grams per cc. And again, we want to make it look like the rest. We can do this. In fact, the other way we can do this is come here, do this, take that, and do that. There. We painted the formatting up. So the density equals to have a cell that's going to be a calculation. And now we want to divide the mass divide the volume. Enter. And again, that's a lot of decimal places, so we'll reduce it to, I'm going to reduce it to 3 in this case, and I'm going to fill down. So here is my density. You can see that it varies a little bit. We could even find out how much it varies by. In fact, I'm going to do that in a second. But first I want to do the delta density. Insert, symbol, insert, close. Density, alt, enter, parentheses, gram per cc, close parentheses, enter. And again, I'll use the format painter to fix that. Oops. So I need to make this a little wider to make that stir then. Yeah. So here we have to go back to our web page, and we'll go down and look for division. Trigonometric functions. Where's division? Multiplication. Division. And there you have it. X over y is that same kind of structure divided by y squared. Okay, so again, I'm going to implement that here. I'm going to say equal and square root SQRT to open parentheses, and here y is the denominator, so that's the volume. So I'm going to take this times the uncertainty of the volume, which is 0.4, times 0.4, close the parentheses, to the power of 2, add the next term, and that's going to be the volume. I forgot the parentheses. Parentheses, volume, times the uncertainty of the mass is 0.005. Close that, to the power of 2. Close the parentheses and divide by y squared, which is the volume, to the power of 2. And I hit enter. And again, I've got a lot of decimal places here. I'm going to tame it down a little bit. And I'm going to fill. Okay, so now I have the uncertainty for each of those calculations. And let's look at this again. The largest one is 0.1. The smallest one is now 0.8. That's exactly opposite to what we have here. So how that calculation worked, the calculation that your indirect measurement that you're making, determines whether the higher or larger sample is going to be have a less uncertainty or more uncertainty. You think about that, get it straight in your head. The size of your sample will determine how much uncertainty you have. In the case of our masses and lengths, if you're going to do the volume, then you want to do it with smaller samples, because that has the smaller uncertainty. If you're going to do the density, you want to do it with larger samples, because that has the smallest uncertainty. Now, we don't have that option here. I have the samples I have, and that's what we're going to do. So what uncertainty do we use? You should always go with a worst case scenario, unless it's an outlier, which means an order of magnitude difference. But for our purposes, we're going to look at the density. I'm going to go with the highest uncertainty is 0.8. So that's what we're going to go with. The uncertainty of the smallest of the samples. Okay, so now we go to procedure 4. Procedure 4 is the same data on the same parts, but this time we're going to do something a little bit better than the ruler, and it'll give you something to compare with the ruler data. These are calipers. You slide them along here. This is a vernier caliper. You really can't see the one, and I'll show you in the next one. The problem with this one, like the plastic ruler, this is stamped metal, it's poorly constructed, it's only marginally better than the ruler, and it's not worth using. This is a much better constructed vernier caliper, and you can actually, can I show you the vernier? The long bar, the one here, gives you centimeters, and then there's the secondary one down here. That's the vernier scale. And you can use that to give precision down to, you see it's stamped there, is 0.05 millimeters. which is pretty good. And these are quite accurate, and we've used them for years. But we're moving on. This is a digital caliper. It does the same job as the other ones, except this one's digital. It's your next sensor. So I can turn it on, I can set it to 0 as 0. If it's not at 0, I can actually have a button to change it to 0. This one's reading in millimeters, and it's giving me hundredths of a millimeter, 0.00 millimeters. So like the scale that we looked at, where's the uncertainty here? Well, it has to be in the next digit. So the uncertainty of this caliper is going to be 0.005 millimeters. And that's what I'm going to use to collect the data for procedure 4. I have a better caliper here. Better in the sense that Mitutoyo is a famous brand for precision instruments. This is supposed to be accurate to 0.001 millimeters. Unfortunately, it still only reads to hundredths of a millimeters, and we can't access that accuracy. It's an oddness that I'm not sure why it exists, but it does. However, if I were to measure the density using this and then using this, and I got two different values, I would choose this one as the more accurate one. But I'm going to save this for procedure 5. So for procedure 4, we're just going to use this to measure lengths. That's not its forte, but that'll come in procedure 5. But we can talk about it anyway. To make a measurement with a caliper, you open up the jaws, slide your piece in, and close it down. Now you should hold it, not incredibly hard, because if you do something ridiculous like this, you can actually affect the motion just by pressing on the wheel because you're flexing the jaws. So you have to be careful about how much pressure you're applying on it. On this side, of course, that's not a big deal. The second thing is this is a flat piece, so it has to go on the flat part of the jaws, right in there. Not the knife edge. Knife edge is for rounded surfaces. So it has to go in here. And 0.27, and if I move around, am I going to get the same value? I am not. 0.2. 0.27. You saw the problem with those narrow little jaws is that you have to have the sample not twisted in any way, and it can be easy to do. So in 0.28, I do have it twisted slightly, and if I play with it, you can see it jumping all over the place. But if I'm careful about it, I'll get down to 0.27. And that's the way I'm going to make the next set of data, using this caliper and the scale. Your job is exactly as I showed you in the procedure 3 portion, and then your analysis will be to compare these two data sets to see if this is what kind of a difference this actually makes. So if this is better than the ruler, then can we do better even than this? And the answer is yes. We can use a micrometer. A micrometer is called a micrometer because it measures microns. I'm going to hold it here, and I'm going to turn it, and 0.277, I go down a little further, 285, 274, 275. Why did I get 285? Anyway, my point is, you see that different points along the sample, I'm getting different lengths. Why is that? Well, the sample has to have an uncertainty in its manufacturing. There has to be a certain irregularity here. And it could be that my 285 was just a bump in the road, or a place where, see, little dent there, that could have been it. So we've gotten to the point where the sample now is adding significant amount of uncertainty. And in order to be able to use this, we would have to measure different places along the length and average them, and we would get a number that would be an average of the surface irregularities. The question here is, do we need that kind of crazy precision? And since the website you're using to look up densities only uses 3 significant figures, the answer is no. So we're going to forgo the use of a micrometer. So now you'll go and do, one more thing I have to show you before we go. In the real world, everything oxidizes. So this is not the color of this. If I scrape this, you see it's a more shiny yellow color underneath. The darker color is the oxide and finger grease, etc., etc., etc. You'll want the color of this to help you identify exactly what it is when you get to the end of procedure 4. And that's it for this procedure. Okay, I told you a moment ago that the flat things weren't the forte of the caliper. See, this one wants to, but I can zero it. There you go. What it excels at is other things. There are many ways to measure things with a caliper. It excels at measuring around things. I can cut across here. Remember, we had so much trouble with doing this with a battery with a ruler? Well, here's the solution. Again, I'm between the flat parts of the jaws. And I'm going to put it at a bit of an angle to make sure that I don't get anything but a diameter. It's important that you be measuring the diameter. If you do this and you're missing the diameter, then you're going to get it wrong, incorrect reading. It'll be an error. So I do this. If I turn it around, I do that. That one's a little smaller. See, this is round, sort of. So in the data, I've gone and given you an average value. I haven't shown you the average value. I've just indicated it in there. The other way you can measure ones, each of these samples has a height. So we already know how to do that. Again, don't hold it too tightly. And each one of these samples has a cavity. So that's a little trickier. Well, actually, it's a lot trickier. These knife edges are designed to fit against the inside of a circular feature. If I want to know the difference, I put it in. The problem is you've got to make sure you're at a diameter. So you've got to wiggle it and try and stretch it out until you get something reasonable like that. And finally, if you want to measure the depth of it has a depth stop. You insert this into the bottom and you close this down until it touches, and then you read it in exactly the same way. This is the trickiest part of the operation, because actually, to be sure that this is flat in there, you should measure it in several places. But again, I've given you an average value that will work. So all of the dimensions you need to calculate the amount of metal here and the mass of that metal, so that you can calculate the volume, density, etc., are given in the table in the accompanying document. But I've played a dirty trick here. Hidden in this data is an anomaly. And based on what you've learned about uncertainty, you have to do some detective work and figure out what's going on. I don't want to give it away. There'll be some explanation in the document, but that's your job. You'll calculate the volumes, the density, you'll plot it, and you'll see what you have to do to make sense out of this set of data. And that's it. Lab is over. Good luck. I'll see you in a few days.